Hi, everybody, and welcome to our webinar on amping up real-time query on data lakes with ClickHouse and Project Antalya Swarms. My name is Robert Hodges. I'll be one of your presenters today. I'm joined by Alexander Zaitsev, who is CTO of Altinity. I myself am CEO. But we're both pretty interested in databases and have done a great deal of work on this. So we hope to present what we've accomplished and give you a chance to try it out yourself. So before we dive into that, I would like to just talk about a couple of housekeeping things. This webinar is being recorded. You will get a link to the recording as well as a link to the slides after the recording is done. It usually comes within a few hours. So you don't have to scramble frantically. It's all coming to you. Second thing, we do have plenty of time for questions here. You can type them into the question and answer box, which is available on the little control bar that Zoom provides, or you can type them into the chat. We don't really stand on ceremony. And if it's a question that's interesting, we'll try to answer them as we go along, but we should have some time at the end to answer your questions as well. So with that, I'd like to dive in. Let's talk just a little bit about Altinity. You may have heard of us. We have been in business as a provider of support and cloud operation for ClickHouse since 2017. Our two main products are Altinity.Cloud. It is a popular cloud platform for ClickHouse. It was the first to run ClickHouse in the Amazon cloud, as well as GCP, as well as Azure, as well as Hetzner. So we've been really pushing the envelope on this. Shared by a bunch of customers, runs not only in a SaaS model where it's running in our account, but it also has a very popular BYOC offering where you can run it in your own account. So something that you can check out after this call. We also offer enterprise support for those of you that, and there are many of you who love to run ClickHouse by yourself. You can run it anywhere from the Amazon cloud to your own on-prem locations, to run it in phones. Doesn't matter. We will provide support for you and help you do it better. All right, enough advertising. Let's dive in and have some fun. So for those of you who don't know ClickHouse, here is a very quick review. It is a famous real-time analytic database. In fact, it's probably the most popular open source analytic database at this time. It has about over 40K stars on GitHub. It's a vanity metric, but it also happens to be about the same number as Spark, which has been around for a lot longer and is also very popular. Why is it that people have adopted ClickHouse? Well, you could think of ClickHouse as being kind of a mix of the best parts of MySQL and a traditional data warehouse that is designed for scalable, fast reads. So from the MySQL side of the house, we have things like understanding SQL, being able to run practically anywhere. When I said you could run it on phones, I was not kidding. It runs great on ARM, and you can do, anywhere that Linux can run, ClickHouse can run. It's also open source. In contrast to MySQL, it has a more permissive license, the Apache 2.0, so fewer restrictions on what you can do with it and how you have to notify users. From the analytics side of the house, we have a shared nothing architecture. That's something we're going to be talking about in this talk because that is where you have a bunch of nodes with attached storage. One of the things that ClickHouse is doing is evolving to use shared storage, but this shared nothing architecture is a very powerful feature and very, very fast. It stores data in columns. That's practically de rigueur for any analytic database in these days. It allows much more efficient I/O, allows good compression, and a number of other benefits that enable you to store data compactly and query it quickly. Speaking of quick query, parallel and vectorized execution, and then it scales to many petabytes. So even early on, ClickHouse was already well into the petabyte range for some of the outliers, including companies like Cloudflare, which adopted it around 2017, posted on their experiences, and were a big influence on getting ClickHouse started in the North American market. So that's ClickHouse. And let's talk about ClickHouse and how it's doing today. So ClickHouse was a huge advance when it arrived. And one of the reasons was that it, as I said, it did store data very, very compactly and could query it, in some cases, hundreds or even thousands of times faster than Postgres or MySQL. This is because of the arrangement of the data and the fact that we have parallel query. But what's happening today, so we're now 9 years on since ClickHouse was open sourced on GitHub, data sizes are beginning to outstrip the capacity of open source ClickHouse. So back when I started working on ClickHouse, which is at the beginning of 2019, it was pretty rare for us to have a customer who had 100 terabytes of data. We now have customers who add 2 petabytes of data per day to their ClickHouse clusters. So this is a vast increase, really an exponential increase in the amount of data that people are putting in, and it's beginning to cause some problems that have practical effects for people who want to use ClickHouse for real-time analytics. Specifically, it's making storage and compute way more expensive than they used to be. So the shared nothing architecture that ClickHouse has uses block storage. So these are ordinary file systems which ClickHouse which are attached to the nodes that the ClickHouse server is running on, and then to provide HA as well as to allow more users to query the data, ClickHouse will replicate them. So that's built in and works with minimal effort, easy to configure. The big problem is the block storage is very expensive. So if you're using EBS, which is popular block storage out in the cloud, by the time you get around to replicating it, it is over 10 times more expensive than using Amazon S3. So that's problem number one, that people, as they grow into these very large petabyte scale data sets or even hundreds of terabytes, storage becomes a dominating cost in the operation of analytic clusters. The second is that ClickHouse has a nice model for operation in the sense that there's a single binary that you run that does everything. It does inserts, it does merges, it does mutations, it does queries, of course. But the thing is that these are all running inside a single cluster. And as a result, you need to have that each of the nodes sufficiently provisioned so that they can handle all of these things potentially simultaneously. This leads to over provisioning and wasted resources. So the second problem that we have is that ClickHouse is increasingly using or allocating more compute than it really needs at any given time and doesn't have the ability to scale it up and scale it down quickly. I want to emphasize this is open source ClickHouse that we're talking about here. These features are available in certain clouds, but if you're running open source ClickHouse, either yourself or with a vendor who hosts it, this is going to be a problem that you will face. So we ran into this, and this is something that is we have hundreds of customers, and many of them are seeing this problem as their data set sizes grow. So, well, as engineers, our job is not to complain about these things, but to do something about them. And specifically, what we're doing is something called Project Antalya. And what we are doing with Project Antalya is solving the storage problem, specifically to allow ClickHouse to use shared data in object storage and to also have a flexible separation of storage and compute. So Antalya is an extension to ClickHouse. It's run out of our own repos that we use for our Altinity stable builds using the same CI/CD pipelines, and it consists of a bunch of extensions to ClickHouse capabilities. You can think of Antalya as a branch of ClickHouse. That's literally what it is, that we build off and contains these useful capabilities. The first thing that it's doing is we're adding Iceberg for shared storage. So if you have used ClickHouse Cloud, you're probably familiar with shared merge tree. That is another type of shared storage, which is based on the merge tree table format and runs in the ClickHouse Cloud. What we are doing is integrating Iceberg, which is now widely used as a standard for querying data. And in addition to being available out on object storage, which is cheap and globally accessible, it can be shared with other applications because the standard is open and anybody who has an appropriate library can read it themselves. So that's a really important difference and a reason why Iceberg is a very good solution for this shared data problem. The second thing that we're doing, and we'll talk about this a lot today, is we're adding swarm clusters. So swarm clusters are where we do the compute storage separation and allow you to just pour on additional compute capacity to make queries on this shared data run faster. And then the final thing is this is 100% open source. So anything that we talk about today is something you can just grab the build, you can see the code, you can change it, you can bend it to your will. Um, our business runs our basic philosophy is that the building blocks of of these analytic systems are fully open source, and what we do as a business is manage them and support them. So that's Project Antalya. Let's dig into a little bit of depth. So what we want to do here is show you what the capabilities are, and then give you some very detailed guidance on how to use them. Plus, we're going to talk about some stuff that's coming down the pike in the next month. So when you set up a system that is going to use shared storage, you're typically going to be running in the cloud. And so here's an example of a shared um, SaaS deployment, or excuse me, a SaaS deployment using Amazon. And for that, we're going to run on Amazon EKS. So Kubernetes, as many of you are aware, is a very popular way to run databases in the cloud. Our cloud, our Altinity.Cloud is built on it. We also wrote the ClickHouse operator, which many of you have used, or properly speaking, the Altinity operator for Kubernetes. So what we're going to do is use this to set up samples. So the way that you do this is if you're running on EKS, for which we have code examples today, you are going to set up an EKS cluster that's managed Kubernetes, which is going to be attached to appropriately to compute storage and networking resources. You're going to install the ClickHouse operator, and then you may optionally add Prometheus and Grafana to allow you to monitor, but we'll leave those out today and get to actually setting up ClickHouse and Keeper. So let's see how we do this. It's pretty simple. So we have a project called Antalya Examples. This shows you how to run Project Antalya. It has documentation, it has code samples for configuration, things like Terraform, things like Kubernetes manifest, Docker, so on and so forth. And so the first thing you do is you just clone this. You just clone this project. And then for the first step, if you're bringing up Project Antalya on Kubernetes and you have an Amazon account, you're just going to CD um, into the Terraform directory where we have a Terraform script, and you're just going to run init apply, and off it goes. And then you update your kubeconfig. This is, again, if for those of you who are working on Amazon, these are probably familiar commands, but there are similar commands available for things like GKE or other systems. So that brings up the basic, sort of the basic um, platform. And now we're ready to dig in and actually build a Project Antalya cluster. So before we do that, I'd like to look just in a little bit more detail on how Project Antalya works. So this is the typical configuration that we support, where we start with a ClickHouse cluster, which in most ways is exactly identical to ClickHouse as you know and love it today. It can do everything that you can do in upstream ClickHouse. One of the things that we're very focused on is that as we add these additions, we want to maintain 100% compatibility with ClickHouse. We, of course, support regular ClickHouse as well, so it's in our interest to do so, and we think it's in the interest of the community. What this ClickHouse cluster does, though, is it has extensions so that when we're reading data on Parquet out on object storage, we can delegate the scans on those files out to the Swarm cluster. So the Swarm cluster is a bunch of stateless ClickHouse nodes that register themselves when they come up, and we use Keeper to do this. So as the Swarm cluster comes up, it has a path inside Keeper that it goes to, and each of the servers just says, "Hey, I'm here," and registers its host name. And then the ClickHouse cluster that on the left, which receives queries, can actually then use that information to find out where the Swarm cluster nodes are, so that it can send the queries out. And then, of course, everything beyond that is just, okay, delegate, do the planning and delegate the scans out to the Swarm cluster, which then looks at Iceberg data, or even directly on S3. So that's how this works. Let's step in a little bit further and actually set one up. So if you want to do this yourself and you've set up a ClickHouse cluster, this is what you do next. You're going to go ahead in and you just as a manifest directory, and you have 4 files that you need to run. These are adapted for Amazon, but in a few minutes you can change them to run on any other Kubernetes you like, including something like Minikube. And then you're going to go ahead and once this has come up, you'll test it out. This is just a command that allows you to log in and just make sure that all the nodes are up and can see each other. So setting this up for anybody who's basic, has basic Kubernetes knowledge is quick and easy to do. All right, let's look into some details. So what you're looking at on this slide is what's called a ClickHouse installation resource. This is the basic resource that is managed by the Altinity operator for ClickHouse. And this is defining a cluster. In this case, it's a swarm cluster. And if you've used the operator before, what you'll find is these definitions in most ways are completely identical to a regular ClickHouse cluster. You won't find, we didn't have to make any changes actually to the operator to support this. One key thing is that they only have shards. So shards are separate ClickHouse servers, which are not connected by replication. So there's just a single replica per shard. And if you want to make the swarm bigger, you make that number, you either change that number when you first set it up, or you can go in later, edit it either up or down, and Kubernetes will accordingly change the size of the swarm. And then we have a reference to Zookeeper, which we use for auto discovery. That's the thing that allows the swarm nodes to register themselves and for other ClickHouse clusters to find out where they are. So this is the setup. It's very simple. There are examples in the Antalya examples that show you more of the details, like how to do storage. So here's one other detail. You may be wondering about auto discovery. If you haven't used it, it's a great ClickHouse feature, which we extended so that you can actually have multiple zookeepers. You can use one for replication, and you can use an additional zookeeper that's just for this purpose to register the swarm. And this is the configuration that you need to add, where you allow cluster discovery, and then this discovery tag just sets the path that we use in Keeper so that everybody agrees on where to go register themselves or where to look if they're trying to find out where the swarm is. So this is pretty simple to do. Again, the examples show you specifically how to do this. So let's look a little bit more closely at the query model. So once you have set this up, you can begin to run queries out on data that's out in object storage. It can either be just files on S3, it can be files on S3 that use Hive storage format, where the partitions names are baked into the file path, or it can be Iceberg, which typically stores information in a catalog. So here's how it works. This is a query that is running on data that's stored in Iceberg. And this will arrive at the native ClickHouse cluster. And what that cluster is going to do, whichever node that gets it, that's going to be your initiator. It's going to plan the query. So it will go look up the metadata for the table that you're querying using the Iceberg catalog in this case. So find out what are the files in the table, what are their partitions, so on and so forth. And then from that, it will make a plan to say, hey, we need to scan the following files to fulfill this query. Those requests for specific files or groups of files get delegated out to the swarm cluster. That's responsible for going and finding individual Parquet files. This is all optimized for data on Parquet, and pulling that data in and then feeding it back to the initiator, which then does the usual merge and sort and hands it back to the user. So that's a very simple one in this particular case. There are more complicated ways that you can set this up. For example, you may want to make these initiator nodes bigger. You may want to have separate groups of them. These are all details that you can work out for yourself. But basically, when you set this up, this is the architecture that you're going to use. There's an initiator, there's a swarm, and then there is there's Iceberg, which is supplying data. So that's the architecture and the plumbing that's behind it. So let's just illustrate this with a couple of different queries. The first one is a query directly on Hive tables. So once again, Hive tables bake the partitions. So tables are divided up into partitions in Hive format. The partition column and the value of that column are baked into the path. And so this is an example where we are querying on a Hive cluster or excuse me, a Hive table. And here you can see we have this special uh, setting called object storage cluster. That's the name of our swarm. So we give it a swarm name. And we have another setting which just says it's kind of like max threads. It's the number of nodes to use out of the swarm. If you don't say anything, we'll just default to using all nodes that we can find. And so this will run your query. And the reason I bring this up is it sometimes is convenient to set groups of nodes, but another thing you could do is you can also have different swarms that people can use for different purposes. But that's basically how this runs. You can't really tell what's going on under the covers. It will just run this query and the results back to you. But in fact, underneath, we're distributing it out to potentially many servers. So let's talk about Iceberg. So with Hive, we just go straight to S3 and we take the data as we find them and kind of infer the structure, or if we're just doing plain Parquet files on S3 with no structure, we just open them up and look for ourselves. Now, Iceberg solves this or makes this much easier because it stores it basically has a way of defining the metadata for the files and saying which ones are in the table, what are their partition keys, what is the current state of the table. So there may be different, sort of the table may evolve over time. So one of the things that's really cool about Iceberg is it has what's called time travel. It shows the state of the table over time, and you can go to different versions of it. So Iceberg, though, when you're first looking at it, one of the things you have to get over is there's no database. Iceberg is really like database storage, which has been detached from the database and then made available to you through an open protocol that everybody can read and access. And so that's defined in the Iceberg spec, which describes how the metadata is managed and the process for doing things like adding files or changing them. And so the catalog in you can read the metadata files directly, but most people use a catalog, which is in the examples we're going to show is a REST server, which allows you to come in, ask which tables are available, what is the metadata of these tables, so on and so forth. The table files themselves are actually stored out on S3, as is the actual metadata contents for Iceberg itself. So, and in this particular example, I show a Python data science app. So that has libraries to read Iceberg, like PyIceberg and PyArrow. Those can read Parquet. And when they're doing reads, they will read the Iceberg metadata, and then they'll go select the files that match. ClickHouse does exactly the same thing. So it has files, or it has code that can read Iceberg metadata. It has code to read Parquet, and of course has code to access S3. All right, that's Iceberg. So we get this set up, we do queries on it. First thing we want to do is we want to tell ClickHouse about this. Um, so the thing that and for ClickHouse, it thinks of a catalog as really a database. In fact, databases and catalogs are really the same thing. It is a list of tables. So when you are connecting to ClickHouse to Iceberg, what you're going to do is define a database, and this shows the command to do it, and it's going to point to the catalog. And then we have some settings here saying that, for example, the catalog type is REST. This is just a standard setting, which you'll almost always use. And then some information about, hey, where are the actual files located so that we have a path that we can go to, and some authorization information. We are using a bearer token. In this particular case, you can also use basic auth as well. There's other mechanisms as well that you can use. And then once you've done that, these then become visible as ordinary, as if they were tables actually inside ClickHouse itself. This is totally cool. One thing to notice is see how these have double-barreled names inside the database. This is a little bit of an anomaly because ClickHouse, or excuse me, Iceberg allows files to have multiple scopes on them, something that ClickHouse doesn't understand. So as a result, when you actually go to query this, you're going to have to put those double-barreled names into ticks like this. By the way, the data set that we're using here is this really great Amazon public blockchain data, which is available out on S3. We use that for testing. It's all in high format. Really great way if, when you're bringing this up to just test things out quickly. As we'll discuss shortly, we are also putting together tools, or going to be releasing tools that will take that data and put it into your own Iceberg catalog so that you can have your own copy. So once we get to this point, now when we're querying this data out on object storage, it looks just like a table inside merge tree, except that we have these double-barreled names. Everything else is the same. We do have this object storage cluster equals swarm to tell how to get the data. So that is how we get to Iceberg tables. One thing I want to emphasize, because this is coming up in the comments, and thank you for folks who are chiming in. Right now, we only do reads. We are working on writes as hard as we can. We're sort of halfway in. We can talk a little bit about that at the end, but writes should be available in a little later this year. All right, let's talk about a really important topic for reads, and that is caches. So object storage is great, but if you have to go to, every time you read it, if you have to go to object storage and download the files or parts of the files every single time you run a query, things will just be catastrophically slow. Moreover, one of the dirty secrets of object storage is that, at least in Amazon, you are charged for API calls. So if you keep banging on the S3 API, one of two things will happen, maybe both. One, you could get rate limited, in which case you'll just start getting errors because you're sending thousands of queries. The second thing, and this is the more serious one, is that you could get a huge bill from Amazon because everybody thinks of this as being cheap to store, but it's also you pay to access it. So reducing the number of calls to uh, both the performance hit as well as the cost of making these API calls is job one to make this stuff run correctly. We have a bunch of caches that do this. So for example, when we're looking at the query planning that's going on in the native ClickHouse server, or the initiator, if you will, a couple of important caches that we use are, first of all, we cache Iceberg metadata. It turns out that Iceberg metadata it's stored in these quite voluminous files that are stored in that have JSON format. It is slow to parse. So if you have to reparse it every single time you do a query, it adds a huge amount of overhead. It can be seconds in some cases. There's another important thing if we're querying files on S3 in high format or just lying in S3 with no structure. Listing them is also a very expensive operation. In S3, there's something called list objects v2, which is notoriously slow. So being able to cache that is important as well. So those caches are available and can speed things up. The swarm itself, there's two very important caches that it uses. It caches Parquet metadata. That's things like min-max and Bloom filters, as well as schema. So that means that we don't have to reopen the files every single time to see what's in them. And then there's an S3 file system cache. This is a great cache that's been around for a while. In ClickHouse, this stores the actual blocks of the files, so we don't have to reread them. And then you can also use external HTTP caches. We're playing around with these. We may have something that we announce later on, but this is another place where you can get huge performance improvements. For now, what we're kind of focused on is building those cache effects into ClickHouse itself, so you don't have to go get additional products and add them in. So here's the settings to take advantage of these caches. Most of these are on by default, so you typically don't have to set these, although as you'll see, there's some configuration involved. But here's something where we're doing a Iceberg tables. These are settings that you would want to have on to get maximum performance. So to cache your Iceberg metadata, cache your Parquet, cache your S3 blocks, as many as you can. And then Iceberg partition pruning takes it goes ahead and takes advantage of that Iceberg information to drop partitions if it can. These things will all speed up queries enormously, often in some cases, by a factor of 10 or more if your tables are very large. If you're going straight against Hive or plain S3, you're going to want to, well, if you're using Hive partitioning, this is a setting, use Hive partitioning, but this use object storage list objects cache. That's a really big one. And in some cases for queries that scan very small amounts of data out of a large collection of files, they can boost the speed by 100 to 1 or more. So, so these are important to have. One final thing on caches, you do need to do a little bit of setup for the file system cache. This shows you how it's done. This is the syntax that we use to put it into into a Kubernetes resource definition. So here you have the location of the file system cache as well as its size on disk. And this is a reason why the Swarm nodes do need to have some storage so that they actually have the cache space. The key thing here is that we are storing it on disk. It's actually, what we're really trying to do here is put it on disk so that it is available in the buffer cache, so it actually gets cached in memory as well. That's where things really get speeded up. One final setting, as you can see, these query settings can be complex over time. Our goal is, of course, to make you not have to know about these. But for now, when you're trying it out, you may have to know about these things like the location of your cache. So a great way to solve these problems is to put them into profiles, which means that users get them automatically and don't have to think about them. And this is just an example of how you set up an XML profile. There are other ways to do it, of course, as well. With that, this is the basic sort of low to the ground treatment of Swarm clusters. I'm now going to turn it over to Alexander, who's going to talk about a big initiative we have, which is, of course, to get this to work in a cloud so that this stuff sets up automatically with a push of a button, as opposed to you doing a bunch of low-level tweaking. So, Alexander, over to you.
Thank you, Robert. Hello, everybody. So what I will go into explain and discuss is how to integrate those features in the cloud, and I will show you a preview of Altinity.Cloud integration and some other features that are applicable not just to Altinity.Cloud, but to any cloud user with Project Antalya. So let's start. So as a cloud provider for ClickHouse, we of course help users to operate ClickHouse with the least possible effort, and we started to bake in Project Antalya features into Altinity.Cloud. So this is a preview. So in order to launch Swarm, it's just you just need a name and instance type and a number of nodes. You can configure spot instances in advance. So if we configure that this C7G is a spot, then it will run on spot if those are available. What it really does, a lot of what Robert just explained a few minutes ago, it starts registries, creates a registry in ClickHouse Keeper. It uses the latest Antalya build available to the moment. It configures Swarm for the best performance, enabling some features, configuring file cache, and it registers Swarm in a registry, of course. Once it's done, we can go to the next slide and enable swarms for your existing ClickHouse server. So say you already have a server or cluster running on Altinity.Cloud, and you want to make it to access the swarms that are running in the same Kubernetes cluster. You can do it just with a single button. And what it does under the covers, it also adds a registry to this particular ClickHouse cluster as configuration necessary to connect to the registry and configure discovery settings. Once it's done, and ClickHouse is restarted, because those changes require restart, you will see the swarm in your system clusters ready to use. Of course, it requires Altinity Antalya build or one of the latest ClickHouse builds for register to work. The next feature that I would like to show you is a catalog. So we have developed our own REST catalog in Altinity.Cloud. It will be open sourced. It's actually already open sourced, but we haven't started to talk about that yet, so it's a little bit unknown. And we make it available for the users in Altinity.Cloud very easily. So if you want to connect your existing ClickHouse, and it can be any build, not just Antalya build, to the catalog, and there's a wizard that tells you how to do it, and basically prints the create database statement. And once you configured everything what you need, and right now we only support Altinity.Cloud catalog, but we are going to extend it to other catalog types, and for different catalog types or providers, there will be different settings. So say if you go to AWS Glue, there will be one set of settings. If you go to some external REST catalog like Nessie, there could be some other set of settings. But for Altinity.Cloud, we already know everything, and we can create a ready-to-use configuration. Once you press connect, the catalog is created, not the catalog, the database to reference this catalog is created in your ClickHouse database. And you can already run show tables and see that there are some tables in this test catalog. So let's go. This is it. Once you created the catalog, you can immediately run queries and run queries in a swarm mode. As I showed in this example, running this simple query with grouping, it takes half a second on a swarm of 5 nodes. If you will try to run the same query on a single node, it will run for something like 20 seconds, 15 to 20 seconds. So this is the easy to use extension of your compute resources to access the data in Iceberg catalog. So let's go next. Some interesting things that you can try by yourself in your deployments. First of all, spot instances. I already mentioned that. If you try to Google for it or read some articles, they typically promise you 90% cost reduction compared to on-demand prices. This is at some extent true, but in reality, the price is variable. It depends on the current demand and current availability, and you can expect something like 50%. So for 50%, you can expect that you can get a discount for spot instances. So this is really good. And they're very quick to scale up, scale down. So it's really a number of seconds, even in EKS with autoscaler. Also, it's very good that you pay for the seconds, not full hours. If you use on-demand instances, you typically run to full rounded hour. So even if you started it for 5 minutes, if you use spot instances, you typically you pay for accurate seconds that you were using the spot instance for. Which is really good for different autoscaling scenarios. If you need to add compute fast for a certain amount of time, you can do it and you can scale it down. We, at some extent, at some point, we plan an automation in Altinity.Cloud that would allow you to scale up and down swarms automatically. But there are, of course, downsides to spot instances. First, they could be interrupted anytime and shut down. So if AWS decides that if somebody requested on-demand instance of the same type, and there are nothing available on the spots, it will randomly select something, not randomly, there are some smart algorithms, select some spot instance and interrupt it, and you will be shut down. And sometimes spot instances are not available. So what would be really cool, and but that would require some careful engineering, is to make a special logic or controller that would be smart enough to fail over to on-demand instance if spot instance is not available. But this is a bit outside of this talk. So let's keep going. Robert, next slide, please.
We have some questions piling up. We'll get to them as we get to the end of the talk and on to the next slide.
Okay, thanks. Some other interesting tips. If you are using an operator, and all examples that we have shown today, they are using ClickHouse operator, then there are some settings that you can tune in order to start swarms faster. By default, operator is tuned for reliability, and it tries to be as reliable as possible to all changes, just not to make sure that cluster never goes offline, to make sure that you don't spend resources without the need, and so on and so forth. But for Swarm, which doesn't need storage, some default guarantees can be removed. And one obvious thing that can be removed is or raised the concurrence ratio. So with those settings that you can see on the screen, you can tell operator to start Swarm with 100% parallelization. That means it will start all the nodes in parallel, and if you request 5 nodes or 20 nodes, it will try to create them all at once. And then it is a matter of cloud provider to provide resources if available. With default settings, it will take longer because it will go one by one, or probably with 50% concurrency, which takes longer. With the new operator version, which we are going to release this or next week, you can already try the image. You can configure it on chip basis. So in your environment, you may have your regular ClickHouse clusters, which use regular logic of applying any changes. But for swarms, you will be possible to specify the max concurrency, so swarms will start and apply changes as fast as possible. Let's go to the next interesting thing, which is performance introspection. ClickHouse has everything built in. So basically, what you need is to build on existing system tables. And the most important system table is query log, of course. In query log, if you run a query or if you run multiple queries, it has a special profile event section which is tied to the particular query or set of queries, and you can use it in order to see what was happening. So this is not a query-specific example. It is just the statistics for today, but you can see very interesting things here, like how many times the Iceberg metadata files cache has been used, how many requests were sent to S3, and our goal is typically to reduce this as much as possible. So when we debug something or when we make performance improvements, we always look into those metrics, trying to reduce interaction with object storage as much as possible, trying to improve cache utilization, cache usage as much as possible, and so on. Also, there's a bunch of interesting things in system events, metrics, and asynchronous metrics. For Iceberg in particular, you can run those queries and you will see all events and metrics that are available. Again, if you run your application, you will be interested in what's going inside. We're going to build a special Grafana dashboards that will help you, but those are going to be based on those tables. We are not inventing anything here. Next interesting thing is how to explore what is inside a catalog. So ClickHouse has virtual columns, as you may know, and those virtual columns often help us to understand what is inside. In particular, using this query, you can check all the paths that exist in catalog. For this particular table, you will see the file names and also the size. You can calculate size of your data, which is not trivial to do if you do it differently. So so you can of course go to AWS Management Console and check the size of the bucket, but you can do it from ClickHouse side. Currently, it doesn't use catalog metadata, which is a bit of a shame. But this data about all paths and sizes, it's already cached and stored in the metadata. So in the future, we will add some extra logic to extract it as fast as possible. Next thing it is actually possible to query the data inside the catalog directly. So those two examples here, one is querying the Iceberg catalog directly, and another one is calling it through a table function. They will produce the same results because they are reading the same data, almost the same data if we have only one snapshot. But you see that inside the warehouse, there's a structure which maps exactly to your schema. So there is a namespace, AWS public blockchain. There's a table name, BTC PS by date. And inside this path, there is, of course, data, and then there are files. When the data is being written in Iceberg, there is no actual requirements on how files should be named and how files should be organized. But if you are writing them using our ICE tool and the table is partitioned, then ICE will automatically create Hive partitioning structure, bucket structure, which is convenient for many purposes. We'll be talking about ICE in the future as well, so this is a great tool. Let's go to the next, and this is what I promised in the chat. So this is a comparison of how you can use Antalya, Project Antalya features with upstream ClickHouse or with Antalya builds. And some features, they work in both places, like swarm discovery or catalogs. Some features don't. For example, if you want to run swarm queries, then in upstream, you cannot use this syntax with object storage cluster, object storage max nodes, etc. You can use table functions at some extent. For S3, you can use table function, but for Iceberg, I actually couldn't create an example how to use Iceberg table function with the authentication scheme for the catalog that we use. Probably it's possible, but it is not straightforward at all because the syntax is completely different. So I would say this is partial support. And some of the caches that we implemented, they were merged to upstream, and some others, they were not merged to upstream. So for example, Parquet metadata cache, which is really important if you query Parquet using S3 table function, it is not supported in upstream. They declined our pull request. Some other things that were also not accepted. So the full set of features, they're only available in Antalya builds. Having said that, ClickHouse team is working hard on catalogs themselves, so they keep improving. And as it was mentioned in the chat, instead of Iceberg, they kind of generalized it as a data lake database engine, which represents Iceberg and other types of catalogs in a single definition. So we will definitely adopt that. With that, let's go to the next slide for our roadmap. First thing that we are going to announce, and it's probably going to be next week, is ICE, which is open source tools for Iceberg REST catalog. So you can use it as a REST catalog. There are a bunch of examples for Kubernetes, EKS, etc., etc. And it is also a tool for loading data, because right now it is not possible to load data to Iceberg directly from ClickHouse, and it's not very easy to do it using other tools. You can use PyIceberg, you can use Spark, but this is all huge infrastructure structures, and it's not very easy to use. So with ICE, you can do it very, very easy. So it's just a command line utility, a simple client. You can give it data, and it will load it to the catalog. The next thing that we're going to announce in June is a support for AWS S3 tables. As you know, AWS last year announced that their own extension of S3, which they called S3 tables, and those are actually catalog managed data. Later on in March or April, they even created the Iceberg REST endpoint or catalog to access this data. Originally, it was only Glue. So our next goal is to test it, and if there are any changes needed for ClickHouse to support it natively, we will of course do it. The UI that I previewed you earlier will be available in June, and Altinity.Cloud users will be able to start swarms, use hosted catalogs inside Altinity.Cloud, and all the features that are available to date. We're also working hard on performance, both on performance testing and on performance comparisons with other technologies. We promised to publish some performance report in June, which will show how Project Antalya stands against upstream ClickHouse or against some other competitors like Trina, for example. The writing story is very important, and this is currently in works. So we are working on write support for Parquet first, and it will go for beta support, write support for Parquet in ClickHouse, and it is the prerequisite to write into Iceberg efficiently in ClickHouse. We know that upstream core ClickHouse team are also working in this direction, so we'll combine our efforts here somewhere about Q3 25. But the main feature which the full Altinity project Antalya stands for is tiered merge tree and iceberg tables. We already started to work on that, but there are many parts to do here. So we expect it to be fully production ready by Q4 this year. What will allow our users is to extend merge tree to Iceberg, and if necessary, you can attach swarms to get faster results from this extension. And that will be done using natural ClickHouse syntax like TTL. So you would be able to write that I want the data which is older than, say, 1 month to go to Iceberg, and it will be automatically moved to your Iceberg tables. But on a query side, you will still be querying them using your regular queries, so no query rewrite will be needed. That's it on a roadmap, and I will pass the microphone to Robert to ramp it up.
Great. So we just have a couple more slides and then we'll get to questions. We can run a little long to make sure because there's a bunch of great topics that have come up. So these are resources. Go to Antalya examples. There's also one thing I want to point out is the code is in our repo. So if you want to log an issue on this, don't log it on upstream ClickHouse. They won't know what you're talking about. Log it on our repo. And if you want to submit PRs, which we gladly welcome, that's where you would go. We also wrote a blog recently. This came out 3 weeks ago. You can also check that out. This gives a lot of the getting started information. And if you want to talk to us, join our Slack. It's the easiest way. If you're a customer, and by the way, welcome friends. I see a bunch of you out there. Of course, you can just talk to us straight through the regular Slack and file support cases. So summary, we've talked about the problem repeated from our previous webinar that we're solving storage and compute costs by extending ClickHouse to use Iceberg as table storage. And I think this is a good time to do it. There's a lot of industry adoption here, and the fact that it is shareable is a huge win because it allows other applications to use it as well. And as we'll see over the years, this enables up completely new architectures that are combine different types of services in very creative ways to build high performance, cost efficient systems. So the swarm clusters, which we focused on today, they are the basic mechanism for compute storage separation. They work now on reads. Writes are coming as fast as we can do them. If you're using them, it's really important to understand caches and to have them enabled. As time goes on, we hope you'll need to understand less and less, but for now it's useful to know what's going on underneath because then you can check if it's really doing what you expect. Alexander showed a bunch of additional tricks from spot instances to diagnostic queries. There's a lot of cool things that you can do. And 2 upcoming attractions for those of you that are Altinity customers or would like to be Altinity customers. This stuff is going into Project Antalya features are going into Altinity.Cloud as fast as we can do it. And ICE is already public, as Alexander said, but we're going to be putting a proper blog article together. A big problem that that we hit and which we think many of you may share is, hey, I'd love to try this stuff out. I've got data, but I now need to stick it into Iceberg. There's a surprising lack of tooling to do this. So we're hoping we cured that problem for ourselves, and we'd like to share that with you. So that's it. Oh, by the way, here's some more contact information. Feel free to tag us directly in the Altinity Slack. One thing I want to highlight is we're going to be doing a meetup at Sentry in San Francisco. So if you're here in person, we'll be talking about ClickHouse and real-time data lakes. Sentry will be there. I hope we'll get our friends at PostHog. Anybody else, in fact, who's working on this problem and is in the area and would like to present, give us a yell. There's definitely room on the agenda to fit additional talks in about how people are using ClickHouse to build real-time query on data lakes. So with that, Alexander, we have a bunch of questions here. I see you're working your way through them. I know there's one that I would love uh, to bring up from Nathan, who had a couple questions. But Nathan, there's one question here I just love. Has anyone looked at using a managed Knative provider, for example, Oz, Fargate, or GCP Cloud Run for running Swarm? I love this question, and the reason I think the answer in answering this, it gives us a chance to highlight two things. One, we have been talking about Kubernetes today because we happen to run most of our stuff on Kubernetes, so it's pretty familiar to us. But everything that we showed you, when it comes to swarm clusters and any of the wiring, this stuff will run anywhere. So you can build these clusters on your phones, as I keep saying. But we've also had discussions about, like anything else that can spin instances up, can create swarms. And as long as those swarms can see the keeper and register themselves, they will become accessible uh, uh, to the initiators when they're beginning to, when they need to delegate queries. So use your imagination. I think one of the things that I find kind of fascinating is Cloudflare workers are another option. We're pretty interested. Cloudflare buckets, storage buckets, recently announced support uh, for Iceberg. So that's another place where we're going to be doing a little bit of digging. But if you have imaginative ideas about where to create clusters, or swarm clusters in particular, let us know, try it out, report what you find, help us fix ClickHouse or fix Project Antalya code so that it works with these types of providers. Alexander, here's one. What happens if a spot instance goes away? Did you test that? Well, we did, and the query fails. So this is a question from Arnaud. I see Alexander is answering it. This is on our to-do list to solve that. Basically, there's going to be, and I'm kind of channeling Alexander's answer. There is a corner case where it's really difficult to keep a query from failing. If you get to one of these swarm clusters and it's giving you results back, it's sort of halfway through passing results back from reading a file. Well, in that case, you have sort of a decision. You either take half-baked results or you fail. We may put a switch in for that, but it's an interesting problem. What we will be doing is adding features that make this more robust, so that, for example, we will, if we connect to the swarm and we find that it doesn't answer before it gives any results back, we will of course just drop it from the list and try it. So that's coming, and should be. Alexander, do you have a time frame for that one? I know I keep bugging you guys about that.
It is currently in development, but
Brilliant.
we just tried to solve some simpler cases. So say
Yep.
when we discovered that some node is not available, when we were playing the query, it's the simplest case, so we can fail
Yep.
over to available nodes. But in general, we cannot avoid failure very easily, or we need. So if Swarm started to stream to the client, especially, then this is already very hard not to fail. Maybe
Yep.
possible, but requires very careful engineering.
Yeah, it's kind of like the problem. What happens if you can't parse something during insert? There's a similar problem. You either fail the whole thing and or leave some kind of mess or just ignore it. So what we'll do is we'll make the problem as small as possible, and then there'll probably be some setting where you can say, hey, I care or I don't care. There are certain types of queries where you actually don't care. Like this comes up a lot in observability where you're just looking for outliers. And if a small part of the query gives you gives you partial results, it's no big deal. So anyway, it's a really good question. Alexander, were there other questions? There was one here. Are there use case level analysis of typical cost performance using this approach versus attached disk versus hybrid? Any links to read this? The answer is we're working on that. I think a big one is, and there was a great article from ClickHouse Incorporated recently on query on Parquet. It showed they're using a particular set, but an interesting thing is just ClickHouse is getting very fast on Parquet. It's now about 2x fast or slower than merge tree, which is except in the case where queries need to use a primary key index, which in which case merge tree still has a big advantage. But Parquet query is catching up fast. I think the interesting thing is to also compare against other databases like DuckDB, like Trino, so on and so forth, and then compare, carefully across all the use cases of merge tree. That's obviously the standard. Um, Here's a question about your own REST catalog. Where do you store the data? Um, and I think the default,
It is etcd.
yeah, etcd. So and it can be made resilient by having multiple instances.
Yep. I would add to the Robert's answer about the cost performance analysis. Uh, if Parquet is only twice slower than merge tree, and there is some room for improvement, but we know that storage is 4 times less expensive when you go to object storage from local storage. So the typical cost performance analysis can give you this 2 times. You can get 2 times better, maybe 2 times slower, but at 2 times less cost. But at 4 times less cost. But you can add extra compute, and that
Yep.
will compensate your slowness.
Yep.
So yeah.
And that's where exactly. So that's where the swarms are such an interesting idea because they allow you to, if you want better performance on the long tail, for example, when you're, in the future when you're able to tier this stuff out to Iceberg, you just pay for it by putting more stuff into the swarm. Or if you have something, like a specialized set of queries, for example, there's a lot of people here on this call that run trading applications. You need fast answers during the day while markets are open. So you spin up a swarm that is designed to do that, and then you can spin it back down as soon as the trading day is done, and you're no longer so latency sensitive. So those would be ways that you could do this. Let's see, Alexander, any other questions? We had some. Let's see, how do you write iceberg tables? That was covered. Parquet files. Yeah, so does the project have an immigration tool to convert CH data to Parquet? Yes, that's one of the things. Sasha, does ICE already do that? Can it dump merge tree out to straight out?
Straight not, but you can stream merge still to the iceberg using ice. I think I answered most of the questions in the
Okay,
chat
great.
below.
Good. Then if there are any unanswered questions, please join our Slack and come ask them to us directly or contact us. If you'd like to sign up, get yourself signed up to try this stuff out in Altinity.Cloud. It's coming really fast. That's going to make a lot of this stuff very easy to access and use. So go ahead and contact us. We will mark your name down and get you set up for this as soon as it's available. And with that, I'd like to thank everybody in the audience for attending. It's a real pleasure to see the enthusiasm around this and to hear these great questions and ideas. Please do join, help us make it better. And Alexander, thank you so much for helping on this webinar. It was a real pleasure to work on it.
Thank you, Robert. Thank you, everybody.
Great. With that, have a good day, everybody, and we hope to see you soon working on an Antalya cluster.